Hello, everybody. My name is Cherdantseva, and my today's talk is named Caught in the Moment, CO2-rich fluid exsolution from magmatic sulfides in the middle crust. As you all know, magmatic sulfide systems form due to partial melting of mantle and released metals, economically important metals such as PG, gold. They are transported by hot high magnesium magma across the lithosphere in the form of dissolved ions or nanoparticles. And in the most common scenario, if silicate magma enriches sulfide saturation, these metals will be separated with sulfide liquids and transported with it. And apart from metals, magma also contains silicates and also volatile phases, despite the fact that it was denied for a long time. And commonly, these volatile-rich phases are found in association with metal-rich phases, which led to conclusions that probably volatiles could play a specific role in transportation of dense liquid being very buoyant. And following the recent publication of Daryl blanks, we know that the main agent of which is responsible for transportation of sulfides and metals from mantle is a CO2 supercritical liquid. And this conclusion was made based on the paragenetic association of sulfides and PGMs with carbonate phases, especially calcite. And this association is consistent through the crust, and we find the evidences in lower crust and in the middle crust. But in the upper crust, the analogous for this CO2 supercritical fluids appears to be water-laminated fluids, or bubbles, which we already heard today about. These bubbles tend to stick to the sulfide liquid and facilitate the transportation of them upward. Later on, this space, which was made by bubbles, will be substituted by water-rich phases. But we don't actually know what happens between the middle and the upper crust when we see these changes between nature of all these volatile phases. We know that CO2 fluid becomes unstable and insoluble in silicate magma and tend to float away and escape it. But we don't know what the outcomes of this separation. And to solve this problem, we chose to study the Rudny intrusion in northwestern Mongolia, which represents a natural laboratory where we can actually trace the interaction between volatile phases and sulfides. This Rudny intrusion is like a small gabbroid intrusion which contains two units, leucocratic unit and melanocratic unit. And on the basement of melanocratic unit, we identify the ore horizon, which contain sulfide mineralization of three types. In the first outcrop, we find relatively big sulfide globules, which are horizontally elongated and contain these loop textures, and they are hosted in troctolites. This layer is underlayered by more high magnesium and chromite-rich narrow horizon with medium-sized sulfide globules, which are rounded or a little bit vertically elongated. The second outcrop is a prolongation of this ore horizon. We find also troctolites a little bit differently looking, which contain small sulfide globules, also rounded or vertically elongated. And to simplify the reference to these three types of globules, I will call them large, medium, and small. This is the appearance of host rocks which contain mineralization of small sulfide globules, medium, and large ones. And we can clearly see that small and medium sulfide globules, they contain the evidence of quite quick crystallization, because here we see the blades of plagioclase lamella, and here we can see blades of olivine. It means that they can represent the quenching zone of this ore horizon, while the large sulfide globules contain in troctolites with normal magmatic texture. And geochemical composition of three types of host rocks do not differ significantly from each other. A little bit of difference in concentration of semi-metals, which I try to explain later. And considering this, and also the size of intrusion, we assume that all these three types of globules were formed from the same liquid, and all the differences can be explained by local processes. What actually helps to unravel the history of formation of this intrusion is interaction of sulfide liquid with volatiles. For example, small sulfide globules contain these immiscibility textures, which are made by volatile rich phases with sulfides. And these volatile rich phases are represented by chlorine apatite, chloride, and calcite, meaning that at the moment of crystallization, this liquid was associated with chlorine, phosphorus, water, and CO2 fluids. On the contrary, large sulfide globules do not contain any evidence of these immiscibility textures. And actually, but they contain these silicate caps, which are represented by chlorine apatite, chlorine amphibole, and chloride, but do not contain any evidence of calcite, meaning that this sulfide liquid was associated with water, chlorine, and phosphorus. Medium sulfide globules, they contain both features, silicate caps and relics of this immiscibility texture, but they happen much more rarely. So we lose a bit of CO2 here. And assuming that these sulfide globules represent snapshots of three stages of crystallization of the same liquid, we move from small sulfide globules to large sulfide globules. And somewhere here between the quenching zone with small and medium sulfide globules and large sulfide globules, we catch the moment of decoupling of CO2, meaning that CO2 here was entrapped just because of the very extremely steep crystallization. But what actually does it mean? How it affects the history and behavior of metals? Here I represent the data made by laser ablation on distribution of trace elements in base metal sulfides in three types of globules. And we can see that the compositions of medium and small sulfide globules are quite similar. We can see less zinc, arsenicum, selenium, almost no silver, tin. In general, large sulfide globules are a little bit richer in trace elements, but they do not contain any platinum and gold. And the opposite we see in medium and small globules, which contain dissolved platinum and gold in sulfides. And we know that that is quite a big difference. And somewhere here, it coincides with CO2 decoupling. And we know that platinum and gold are incompatible with sulfide liquid and tend to escape it. So probably these two processes are connected somehow. And especially considering that sometimes we find PGMs in spatial proximity with this immiscibility textures in small globules where CO2 decoupling didn't happen. So to illustrate the model of crystallization of this intrusion of this natural laboratory, I represent this cartoon. So we intrude the high magnesium magma, silicate magma with a little sulfide liquid, which coupled with CO2 fluid. And we intrude it in already solidified leucocratic unit. And due to the difference of temperature, we start to get the quenching zone and very quickly crystallized. And we catch here this couple in form of this horizon with small sulfide globules where we catch immiscibility textures. And then we continue to crystallize quenching zone, but we start to decouple sulfide liquid and CO2 fluid. And this decoupling leads to platinum and gold to segregate from the sulfide liquid. And sulfide liquid, because of this loss of CO2, starts to lose also its buoyancy and starts to settle down. And during the settling down, it collects and collect more, get more enriched in PGs and gold and tin and other elements. And when it's landed on the basement of magma chamber, it become horizontally elongated as large globules are, and because of this gravity effect. And afterwards, already at lower temperatures, this water, chlorine, and phosphorus, which didn't escape from sulfide liquid, they escape afterwards and form the silicate caps. So take-home messages from my talk today is that sulfide mineralization of Rudin intrusion represents snapshots of 3 stages of crystallization of metal-rich sulfide liquid. The CO2 liquid serendipitously got entrapped with sulfide liquids due to extremely quick crystallization right before the moment of exsolution. CO2 liquid facilitated the transportation of dense sulfide liquid, decoupling of CO2 liquids led to the coalescence and settling of the sulfide melt. During degazation, CO2 captured platinum and gold incompatible with sulfides. Thank you.